Am I audible on Zoom?
Say a couple of words of introduction.
Okay, so let's continue with our afternoon session. First bad part is that we're running a half an hour late. We missed the schedule, but doesn't matter. We will try to cut that in our proper break. So I'm really happy to introduce Supratik, who is a professor at IIT Bombay, and he's doing amazing work in the in Boolean functional synthesis. When we talked about initially or about the original problem of the church imposed, he was talking about Booleans. And Supratik is actually addressing this talk. He actually wants to say if you have two types of input that are Booleans and there is specification, how do you actually get a program that is computed? So thank you very much, Supratik, for agreeing, and please continue with the talk. So I will give very short introductions because we have to.
Thank you, Vijay. Yeah. And good afternoon, everybody. So I guess I'll just jump into it because we're running short of time. So this is, of course, work with a lot of my students, collaborators. Okay, so what's it all about? So suppose you're at your office table in your morning, thinking that I wish I could have a system that works like this. How does the system work? It has, let's say, 2 inputs and 1 output. And here is a very popular way of specifying how a system works. It's an incomplete specification. But you just give some examples. And this has become very popular. This is programming by examples. I could also give a logical relation between the inputs and the outputs, something like this. Or I could describe in specification in natural language, depends on the setting, what the people you're interacting with. And what I would like is, maybe, so you could look at any one of these specifications. We'll primarily focus on this one where we have a logical relation, giving how the inputs and outputs should be related. And then maybe after some effort, you find out a program like this. And then your colleague comes along and says that, well, how do you know this is correct? And you say, well, I've done automated synthesis. It's a great technology. I don't even need to work. This is what Roderick also mentioned in the morning. So the point is, maybe a couple of months later, the specification changes a little bit, and then you don't want to, scratch your head again and come up with another program, and then your colleague again questions how do you know this is correct. So if you have to do this manually every time, there is this problem that a small change in the specification may produce changes. Not so obvious changes in the implementation, and then you got to go and this verification cycle every time. So wouldn't it be nice if we had an algorithm which could take a specification and plug it into the algorithm, and out comes your implementation, so the correct system. And that's what the morning's talk was also about. And I'm also going to talk about a similar thing now. And of course, now once you have such an algorithm, you can go and change your specification, and then you get into the system. So this would be really nice. And in this talk, I'm primarily going to focus on specifications by logical relations, put it into an algorithm, outcomes the system. Okay, so yeah, so the first observation is that even in the non-sequential behavior setting, non-reactive setting, this problem can't be very easy, because here is a simple specification. It says that there is an input X and there are outputs Y1 and Y2, and let's say the input X is a 2n-bit number and outputs Y1 and Y2 are n-bit numbers. So I want to say that the input is the product of the outputs. That multiplication subscript n means it's the n-bit integer multiplication, let's say unsigned integer multiplication. And my specification also says that the output Y1 should not be equal to 1, expressed as an n-bit number, and neither should Y2. So what we are really doing is we are asking Y1 and Y2 to be non-trivial factors of X. This is basically factorization specification. The point is, you know that the specification is fairly simple. Even if you do it in the simplest way, it's O of n square. Size of n square, you can write down that specification, even if you write individual bits. And the other interesting thing about the specification is that it is not always satisfying, right? For example, if x is prime, you can't do two factors, none of which are 1, such that the product is the prime number. But yes, yet it is an interesting specification. I mean, if you could find a system which could do such things, that would be immensely useful. And of course, an efficient solution to break systems. So we know that this is not going to be an easy task. But let's try to formalize this a little bit more, because here we saw a few things like, the specification may not always be satisfying, and yet it looks like an interesting specification. So what is it that we actually want? Can we formalize this?
So I think there was a question from Sanjiva.
Oh, okay.
You need to click it.
I'm answering it, I'm answering it.
Okay.
It's not addressed to me. Okay. So in this, in the morning, Roderick talked about reactive synthesis, and this is where the system and environment are in continuous temporal interaction. So we talk about infinite sequences of inputs and outputs. Lots of interesting examples, operating systems, switch, and controllers. But that is, so reactive synthesis is not going to be the focus of this talk. I'm going to be talking about what is called functional synthesis, which is what Roderick specifically said he's not going to talk about. It's complementary. We didn't collaborate when preparing the slides, but it's nice. So here the system generates outputs in response to current inputs. There's no dependence on past history. But I will show you one slide on how this can actually be useful for synthesis, how functional synthesis can be useful for synthesis. So we're talking about current input and current output values, and once again, there are enough examples I'm going to talk about. So that's the focus of this talk, functional synthesis, and we have mostly Boolean inputs, in fact, for this talk. Okay, so let's define this problem. So we have a bunch of input variables, call them x, I, and we have a bunch of output variables, call them yj, and we have a Boolean formula on these x's and y's that specifies some relation outputs. And we want to synthesize Boolean functions or programs for each of the outputs in terms of the inputs. So for the output yj, I want to synthesize function fj, which can look at all of the inputs in this version of the problem, and it generates a Boolean value 0 or 1, such that let's first see in English what we want, and then we'll put it down in the notation of logic. So remember the specification for factorization, where we know that there may not exist solutions. But we are saying that, well, if there are values of the outputs that's going to render that specification true, there will be cases where there are no values of the outputs that renders the specification true. But if there are values of the outputs that renders the specification true, then the specification will also evaluate to true if I plug in these functions for the outputs. Okay? So if I write it in terms of logic, I should say that as long as there exists y1, ym such that phi evaluates to true, then phi with function substituted for y should evaluate to true, and then this should hold true for all possible x. So in the literature, these functions are also known as scoring functions, which are used to scoring is a formula in existential quantifiers. So the literature, this is also known as scoring functions. So I would like to emphasize the distinction from realizability here. So here, no specification is bad for synthesis. In the usual sense, we say a specification that is unrealizable cannot be synthesized because there is some input for which you can't have any output that satisfies the specification. So here we are saying, okay, if there is some input for which there is no output, too bad, we can't do anything. Every output is equally bad. But as long as there are other inputs for which that specification can be satisfied, we would like to get it correctly. And, this is basically what I just said, that as long as there are some inputs for which it can be satisfied, this must give the right value. And for the other x's, it's inconsequential. So one might say, you know, what's the big deal? We can take the specification and we can change it to say, you know, as long as exists y1 to ym phi x, I mean, I could make, you know, I could restrict my x's to be only those such that there is y1 to ym phi x. Well, that's true, but then you're talking about a specification which has quantifiers in it. You want to eliminate the quantifiers, that's not easy, particularly if you have many of these outputs. And so what we'd like to do is we'd not like to complicate the specification, like take the same phi that's given to us, but we'd like to guarantee this property that for every input for which there's some output, we'll be able to generate an output. For other inputs, we don't care, because in any case, no output. In fact, this also provides a way. I mean, suppose I could do this kind of a synthesis, and then I give you an x and out comes fx. I can plug in that fx for y inside phi, and if phi value is to 0, then it tells me that there is no y which will work for that x. Because if there was a y which worked for that x, the f's that I have would have given me those y's. Okay. So, you know, there are lots of applications of this problem. Just a partial listing here. Quantifier elimination, of course, substitutes functions, certified QBA SAT solvers, which in turn are useful in planning game strategy synthesis, reasoning, all of that. I'll talk a little bit about how it can also be used to basically compute a strategy from winning region. We have computer synthesis. It's useful in program synthesis, repair, partial synthesis circuits, and so on. And not surprisingly, there has been a lot of work on it. In fact, the earliest connections that we find was related to Boole's work in 1847, when he was talking about unification of Boolean functions. There is a very nice connection of unification with, I mean, this was much before Skolem had even talked about Skolem functions. But you know, a unifier of Boolean functions, if those functions are related in a certain way, can be thought of as a function. Of course, in cases where for every x there does exist a y, so that phi xy is true, you can look at the proof of that of the validity of that formula, and from that you can extract Skolem functions. But as I said, we want to go beyond those kinds of formulas. There are several other techniques. I'm going to focus in today's talk on number 5 and number 9. So number 5 is knowledge compilation, where if the specification is given in a special form, then it turns out that synthesis becomes simple. And the other approach is to guess or learn an initial Skolem function candidate, then check it, and then iterate. Okay, so let me quickly go through some applications before I jump into the main. So this is how much time should I take?
How much time do you? It's talking 45 minutes with questions, right? So we started, let's say, you have now half an hour.
Oh, yeah. So, should I use the entire 45 minutes? Or should
If you want, you can make it shorter, but you can also take it. It's kind of not fair. It's our mistakes, right? You know, don't go over the time, but if you make it short, you won't complain. Okay. So here is an application that I thought I'd highlight, because in the morning also Roderick talked about something similar. It's an arbiter, has an LTL spec, and Roderick actually showed us how this can be formulated as a 2-player game between the system and the environment. And strategy for generating the Y's is a winning strategy. Game. And we can generate a game graph for this. Let's not get into that. But here is the method that he also outlined in the morning, that you first get a non-deterministic Buki automaton, then you get a deterministic parity game from which you extract a winning strategy. And once you have the winning strategy, you can construct a next state output circuit as a milling machine. You can construct a milling machine which has a next state. So it's in this part that once you have the game graph,
extracting a winning strategy and constructing this is where one can use functional synthesis. And this is how it works. This is just, it's not exactly the graph that I showed you, but let's say a general arbitrary game graph. And let's say the parts, the states that are shaded constitute the winning region. So what is the winning region? The winning region is such that once you're in one of those states, you can always make a move. The system can always make a move such that the specification can be satisfied. So there's no way to force the system to lose the game. And so let us say that here the red transitions are the transitions of the system, the green transitions are the transitions coming from the environment, are the inputs coming from the environment. So here what you see is that, if I'm in this state, I have an option of taking this red transition and this red transition, the system. But if I take this red transition, I come to this state, which is within the winning region. And from there, maybe this environment forces come here, and then I have two options. If I take this, I stay in the winning region. That's how I can stay in the winning region. There's one state here. This state should not, this arrow should have been colored green. Either the system takes a move or the environment takes a move. State. So, once you've identified the winning region, basically, this is what we want to figure out. This is what a winning strategy would be. That if I'm in a state and if there exists a red transition to the winning region, I should choose that. I should not choose transition which takes me out of the winning region. So really, this is what we're trying to satisfy, that for every state, I want to find out what should be the why, right? Such that if I find the next state from the given state, so why, then I'm going to stay inside the winning region. So if this winning region is a predicate that describes the set of all states, the winning region, then I want this predicate to be satisfied no matter what state I'm in, as long as there is a y such that from the current state, if I move on the input y, if I move on the system producing y, I stay within the winning region. And then, of course, there might be some states where, from which this formula is quantified about the set of all states. So there could be some states which are way outside the winning region, which you cannot get inside. So we're not really worried about those because, of course, if the initial state is outside the winning region, we've lost the game. But as long as the initial state is winning the winning region and I sort of play by the scoring function I get from this, I'm guaranteed to the state. So notice that when I formulate it like this, there are no temporal operators here. They have all been factored into the construction of this graph. And it may not always be satisfied, as I said, for some states, maybe from this state to here, no matter which way I go, I'm outside the region. But then, as long as the initial state is winning, we don't care. So as long as we get a scoring function for this formula, we're okay. Here is another application in circuit repair. One can also do this program repair. So basically, we have let's say a circuit, and then there are some black boxes which take in some inputs, provide some outputs, and there's some overall specification that the output should satisfy. In this case, the XOR of the inputs. And then we want to synthesize these black boxes such that the overall specification is satisfied. In fact, this picture is taken from some. It's not our paper, it's taken from other papers in the literature. But really, it looks like this: that for every value of x1 and x2, I want to have y1 and y2 such that some relation is satisfied. Fine, x1, x2. And here, as you can see, we are sort of writing down what this is y1 and y2. So once again, what we'd like is these black boxes to be automatically generated such that its overall specification is satisfied whenever possible, and that once again uses. So this is Is that fine? Are there any questions on this part? This problem where we are actually taking we're not putting any restrictions on the specification. We never worry about whether it is realizable or not. Yeah.
I have a question about this application. So you have this spec, and when you so these black boxes, when you produce let's say this preconditions that the spec is that you currently have is unrealizable, then does it mean with the it's kind of trying to nicely formulate. Does it mean that you will try to also repair the existing skeleton that is out there, or you will just kind of try to find things into black boxes that so I'm kind of trying to understand where is the repair process goes. Is it just build black boxes or try to rearrange circuits as well?
So we define the scope of the repair as the part within the black boxes. If we make it a larger scope, then everything inside that can also.
Because then it will kind of feel like synthesize the whole circuit, but maybe this part that is already there, even if it's unset, you could kind of use this as a backbone, right? To say, like, okay, there is some sorts of spec, maybe it's unspec, but if I change maybe this and with or, then becomes a spec, because I'm kind of referring to it wasn't really about circuits, but I had a student who was working about repairing expression. And he would have expression that would not type, but he would nevertheless, even though it wasn't really typing, he could kind of extract this backbone, which actually means the thing that you already have is some sorts of backbone, and then you see how easily, if it's
minimal
unset,
changes you can produce.
Yes. So, that's why I said, like, I try to nicely formulate first. If things is already not, it's unset. That is okay. You can't see this in the black boxes, but you have some sorts of things already given here. So you actually want to see this, an outline that they have. How much I can change that they still synthesize something that can repair.
Yeah. So I think.
Replace all the panel with black boxes.
Yeah, exactly.
Try and
this is maybe too much because
but try and make as many of them as flow through.
So it's like hard constraints and soft constraints.
Yes.
So currently here there are only hard constraints.
Okay.
You can't change something and you're fully allowed to change something.
Okay.
But I guess what you're talking about is something intermediate where if that works, if you can make that work well and good, otherwise what is the change?
To try to give better explaining, but maybe I understand from the software perspective, I think it's really kind of a nice thing to do. Like, let's assume you want to open file in Java, and then you need to put like buffer something, you put all these things, but actually maybe you forgot to add one parameter. And even the discussing compile, you already have enough input to understand how to repair. So when someone provides like somehow this is like a sketch, this is what they need, and then maybe in the rush replace and with or it actually this skeleton is like not for nothing, right? The person who put skeleton had something in mind.
Yeah.
And then it's the question like how much you can use this, even if like they provided some sorts of skeleton, it's like how much you can change this so that it's still that's why I say how I'm trying to understand how.
Yeah. I think that's a very interesting application, and
okay,
we haven't tried that, but yeah, if I have time, I want to demo or two. We can actually try these kinds of things.
Yeah, we can take it longer so we can try this.
In fact, when Rajiv teaches this atomic theory class, they have a grader actually finds the minimal correction needed to solve the problem or the solution given by the student. But the grade is actually based on the
Yes, so let's see. Get to that point where we have time to play around. Okay, so now the question is how hard is this problem? It turns out that the hardness does indeed depend on the representation that you're using for both the specification and the school functions. For our purposes, we just consider specification and school functions as Boolean circuits, negation not form, which is AND gates and OR gates inside, all conditions. And any other Boolean circuit can convert it to this fixed input gates. Okay, so the first thing, not surprisingly, this is NP hard. So what do we mean by NP hard? And this looks like a functional problem. We had talks about a decision problem. But if you think about the problem formulation, we said for all x there exists y phi x y. Now if I make that x an empty set, just becomes there exists y phi y. So I'm giving you a formula and I'm asking you directly, give me constants to substitute y is the formula satisfied. And if I have a Boolean function synthesis algorithm, I can feed this formula there, and it should give me the constants, and I can just plug in the constants back. Check satisfied. So in that sense, it's in the hardness hierarchy, it's at least. For the space complexity, it turns out that unless the polynomial hierarchy collapses to the second level, there will be specifications for which scoring function size is a pseudo-polynomial size, and unless the non-uniform exponential hypothesis fails, there will be functions for which scoring function sizes are exponential. It doesn't matter how much time you take to. So, I mean, this is kind of, in some sense, bad news because it's saying that well, efficient algorithms are unlikely. But then, then we don't give up. We don't throw up our hands. We say, okay, let's try to see what we can do. And that's what I'm going to discuss. So here is a kind of 101 of Boolean functional synthesis. Let me try to show you that some cases are really simple, and we introduce the more general case to the simple cases. So the one output synthesis, where there's just a single output given, this is actually easy. In fact, we can directly say that given the specification, you substitute 1 for the output, and then you get a function in terms of only x, or you substitute 0 for the output, you get a function in terms of x and negate that. And both of these suffice. And this might look a bit mysterious. How does this work? So we can just quickly walk through one of the cases. So suppose I choose phi of x1 as my candidate function. Note phi of x1 is just a function of x. So then if for some x, if phi of x1 is 1, then if I plugged in phi of x1 in place of y1, then phi of x of phi of x1 is for that x1, x1. Phi of x1 is already 1, so 1. And if phi of x1 is 0, then this formula reduces to phi of x0. And because phi of x1 is 0, exists y1 phi of x1 is indeed phi of x0. And this is just doing case analysis. But this just shows that I can just take this thing, I can look at the spec, stick in a 1 for this output variable, and I only use scope function. So legitimate scope function. And I can do a similar case analysis function of phi x0. And in fact, what we can show is that all possible scoring functions are interpolants between the scope. Any scoring function is from this. So this is in some sense the extremes of the scope functions. Okay. So if I had just one output, it's done. I already have a solution. And as Supratik asked, it's not just about finding one solution. How do we find out non-functional criteria for? So here at least we know that the entire space of scoring functions is just the set of interpolants. It's a nice lattice between these two functions, and every scoring function is okay. What happens if we have multi-output synthesis? So let's say I have m outputs. So let's try to see if we can transform it to a one-output synthesis. So of course there will be hurdles along the way. But suppose I constructed a new spec which is obtained by quantifying out the first m-1 output variable. So it has only the inputs x and output ym. Of course, how do I quantify this out? This is difficult in general. But suppose I could do this, or suppose I could even approximately do this. Then I have got a one output synthesis problem, and then I can synthesize x. I can synthesize the function for that yn in terms of x. And then I could just construct a new spec next time where I have modifier out the first m-2 variables. And now my inputs are x and should have been ym, not xm. But I'm treating the ym as a new input and the output is m-1. And I can repeat this process. Basically, I'm saying that what I'm doing is I'm going to eliminate all the other variables, treat it as a one output synthesis problem, solve that problem. And then I'm going to take the next output because I've already solved the problem for this. I can now express it completely in terms of the x's. And then I can just repeat this. So now synthesize fm-1, which is the scaling function for y-1, in terms of x, and the extract xl, which is representing the ym. And then I can just repeat this. So this looks like a very naive way of doing this. In fact, a lot of the techniques really boil down to this. How do we do these manipulations? So it's basically looking like this, that if you can do efficient computation of that existential quantifier elimination, then you can compute the scaling functions efficiently. And of course, in the other direction, it's easy if you compute scaling functions efficiently, just plug them back in. You're very So there's actually an equivalence between these two things. And if a certain representation or a certain algorithm allows you to do that efficiently, then it must also include this. This is the idea that pursue. So let us see how we can try to do this existential quantification with NNF circuits. So here's the specification phi xy. All the x's, the negation x's, y's, and negation y's are in the leaves, and the circuit is just made of gates. And of course, I set y's y1 to 1 and negation y1 to 0, and that is the cofactor. And do a similar thing with the other cofactor. And the existential quantifier is by definition disjunction of these two things. But then, if I want to calculate this existential quantification, this one doubling the size. That's bad. So the question we ask is that, well, can we compute that existential quantifier without the doubling? And to begin with, can we at least compute an approximation? Because obviously we can't do it exactly. So there is this first observation, which is that if I take this circuit as is, and if I rename this instead of calling it negation y1, which forces me to assign values of opposite polarity to y1 negation y1, if I just rename it to, let's say, y1 bar, but y1 bar is not necessarily negation y1, then I have the freedom to assign all the values I want. And for example, if I assign both of them 1, so it's the same circuit, structurally exactly the same circuit, just rename this input and that gives me the freedom to assign both of them 1. Then because the circuit is monotone, because it has only AND OR gates or combinations, I get an over approximation of both of them, and hence I get it. So what will I get here? If I substitute both y1 and y1, that over approximates both of these cofactors, and therefore it over approximates their disjunction, which is the existential. So you see that I can take this circuit and I can actually convert it to NNF. I can rename something, and then I can just plug in constants over there. And of course, that variable goes out, and what I get is guaranteed over approximation. But of course, the other way, in the other direction, it doesn't always hold. And if the other way it held, then it would be done. Right? And so a lot of what we try to do algorithmically is to try to make sure how do we fix the implication in the other direction. Because the implication in this direction always holds. The implication in the other direction is what we like to hold, because then we have obtained an easy way to do quantification and then do synthesis. but of course that doesn't. So the first approach that we took to this is called the guess, check, and repair approach. This is really saying that let's pretend that that actually can serve as the existential quantifier, the result of eliminating the existential quantifier. And in some cases, if it does, then we are fine. We'll get the correct scoping function. We can then check it later on whether it's the correct scoping function. And in some cases it doesn't, then our check should tell us where it fails. Maybe for some values of x it fails, and we'll go and fix it for those values of x. There's a classical check and approach. So guess, check, repair approach. So we guess smartly and efficiently, and this is clearly the come up with when the guess is correct and when it is incorrect, and then we can check if the guess is correct. So I'll quickly explain what that is. Turns out that we can do it using just solver. You don't need to be solver. And then we can use the result of that check to repair our approximation.
What are you guessing?
Pardon?
What are you guessing in the guess part?
So I'm going to guess that. I'm going to guess that that will serve as the existentially, as the result of eliminating the existential quantifier.
That's the choice of y1? Or?
No, I mean, I'm trying to find out x's y1 phi xy, right? Because if I can do the quantification, then I can do the synthesis. But I know that that is an over approximation in general.
But yes, the quantifier eliminated form of that.
Yeah, I'm going to basically pretend that okay, that thing at the top is going to serve as it's good enough for the quantifier eliminated form, and then I'll use a check to tell me for what values of x is it now. And if it is,
that's quantifier.
Yeah. So I mean, it's not a random guess; it's an educated guess. It's a guess where we know that part of the job is already.
And in particular, you're looking for x's where the fact that over bar y1 and y1 being the same value.
Yeah.
Is relevant.
Yes. Exactly. Okay, and the second is the knowledge compilation approach, where we actually try to massage the circuits as that implication. Well, this is the guess, check, repair approach. So we generate candidates colon functions, and I already told you roughly how to generate that. We check, and if their check succeeds, then the output is colon functions. If the check does not, then we use the counter example to compare colon functions and distribute the same. So I've told you, very high level sketch of what this involves. What this involves, in general, we're trying to check, given some candidates colon functions, does this hold? This is the definition of this. This looks like a QBL formula. Looks like we need a QBL stat solver to solve this, but it turns out that we can remassage this formula. And this is what we call an error formula. And if this error formula is satisfiable, it means that equivalence doesn't hold there. And why is that? Because it's a satisfying assignment. So suppose I have a satisfying assignment of this formula. So this formula consists of two copies of phi, one which is negative, one which is unnegative. They share the same x, but they're two distinct copies of phi. So this y and y prime overlap. And these y's are forced to be the same as the candidate functions f for the general check. And suppose I have a satisfying assignment to this, what does that tell me? That tells me that there is a value of x for which I can assign values of y prime, since that phi value is true. So indeed there is an x for which the outputs can be generated to satisfy the specification, but the values of the outputs that are being generated based on the scoping functions are not satisfying the specifications. So these y's are set to f's, set y's to x specification. So if you take the satisfying assignment, then this first part must be true. So it's saying that there is at least one valuation of x for which it is possible to find values of y such that it satisfies the specification. But for the same valuation of x, if I substitute values for y which match what guessed functions are, it does not satisfy the specification. And so this is a problem. This means that our scope function is not correct. And as long as it continues to have satisfying sign, we have a scaling function. And if it is unsatisfied, okay. So
wherever phi of x, f, y fails, when we just negate the output of f.
whatever phi of x,
That's where there's a counterexample, not phi of x, of y, fx.
yeah, that would work for a one output case. If you have a vector of outputs, each one of them is 1, 0, 0, 1. That is the wrong output. That's the wrong vector of outputs. I don't know which one to flip. Yeah, the one is. Okay, so now, okay, explain knowledge compilation, 5 minutes. And then sure, 5 minutes time.
Let's, after this, we should do stuff.
Pardon me?
After this, we should start.
Yeah. So, so this is what knowledge compilation tries to do. That we take our input specification, which could be in whatever form. We take a identification of what are the inputs, what are the outputs, and then we compile the formula into a special form, such that after that, generally scope functions is formed. And it really comes from here. We've already seen that this always holds. So we're asking what is this? So that holds the data. And this actually refers back to a lot of work we've already done. So for example, there's something called decomposable negation of form. It says you take an NF circuit and you forbid certain kinds of paths in the circuit. So for example, you can't have an AND gate, which is both of whose inputs are coming from the same variable, negated or unnegated. So you can't have two paths from YK to an AND gate or from YK negation YK to an AND gate or even from negation. And this has been used in the AI literature. This is one of the knowledge compilation forms. And it turns out that this is sufficient for blank space scoring function synthesis. Turns out that a weaker version of this is also sufficient as long as we don't have an AND gate, which is both paths from YK negation YK. That itself suffices. And then we can generalize it even further by saying that, well, we go beyond paths and just say that, well, at the top of that circuit, you should not be able to realize the function YK and YK bar semantically with some side conditions where all of the left things are set to ones and you're allowed to put whatever here. So this is really generalizing the syntactic condition to a semantic condition. This also turns out to be a sufficient condition. And then we asked ourselves that can we get both the sufficient, necessary and sufficient condition? Is all sufficient conditions, and it turns out that that is also possible. Let me not get into the details of this, but it basically says that you can't achieve something like YK and YK bar at the top under some restrictions on the inputs. And so we've developed some tools based on this. So, for example, this USS, which is based on the district approach, it's a knowledge compiler for this. And I guess I can just summarize by saying that it's an interesting problem on which lots of work has been done, and out of more than 600 benchmarks, you see that things are steadily improving. So we had a AAA later this week is HI. And then to conclude, I would like to quote Byron. This is the virtuous cycle that he talked about, but I'd like to interpret it in a different way. So basically, application area driving. more investment in terms of search energy, time, effort, and foundation tools. And these foundation tools drive for applications. And in the future, quality of synthesis, as referred to morning, beyond. So currently we have the specification is one formula where for each y there is a it can depend on all the x's, but in general we would say that y1 is on subset of the x's and y2 on the subset of the x's. So this would be generalizing into Hinkin quantifiers, and then of course beyond position. So let's stop there.
So,
Demo, but yeah, I'm sure whoever's interested.
So for those benchmarks, were any of those benchmarks similar as the bit vector Cygus benchmarks?
So
Did you use the same approach with those?
yeah, so in fact, not our group, but another group. So they have used the same approach on vector Cygus benchmarks. So on vector Cygus benchmarks, if you say a function, a vector function is can depend on all the inputs, then it directly falls in this class. But if you say that you want to synthesize a program which has two functions, one function falls depends on x1 and x2, the other function x2 and x3, and together they should satisfy something. So that is the dependency QBF based synthesis. So there's also some work there. So these benchmarks are not directly from the Cygus benchmarks, but these experiments have been done only on the Cygus benchmarks, and we'll actually solve.
But that's sort of a subclass of what you're describing. Right. Makes sense.
So this is, I guess, this thing always comes up in discussions with synthesis. That in Cygus you're providing the grammar. So in one sense, you are chaining down what your solution can be, but that grammar also helps in tuning out the search space, and probably what you're getting out of that is more understanding. So you are the one who is deciding. But at the other end, because you're chaining down, you are missing out something that you did not capture in the grammar. And so these are the two viewpoints. And in terms of the actual solutions, the sizes of the solutions, it looks like quite sometimes.
We talked about the getting the image computation. More efficient.
So what if I
actually evaluating that? Morning checking.
We tried to do model checking with this. No, haven't tried. Interesting. In the sense that start with the approximation and then you get down to something.
Or just synthesize this image.
If we go around this loop to synthesize it exactly, then of course it will be exact. There will be some but I guess the point is that most of the times you don't need, because it's, you don't care about all possible x's. The subset of the x's for which you care about. As long as we have it for the check tells you the